Hello, everybody. My name is Camille Thorne. I'm an NLP scientist at Elsevier, and today I'm going to talk about disease normalization with graph embeddings. This is joint work with the University of Amsterdam, the main author being Dhruva Pujari, on whose behalf I speak today. So, to semantically enrich clinical text, we need to detect disease entities. We need to perform disease name entity recognition. But this is a challenging task. Why? Because disease entities are very ambiguous. So typically, you need to additionally resolve or disambiguate these disease entities, solving a task known as entity linking. And these entities will be resolved to so-called canonical names, which are standardized descriptions that uniquely specify a unique disease. They are also known as disease concepts, and they are defined in manually curated repositories known as thesauri or taxonomies, but okay, sometimes they are also found in databases and knowledge graphs. Current systems for entity linking in practice often ignore the graphical structure of such resources. So thesauries and taxonomies, they have in particular a tree structure, narrower, broader than relationships between concepts, knowledge graphs, and even richer one. So the question we tried to ask was whether we could leverage that structure to improve on entity linking using a new gist of neural embeddings known as graph embeddings. We used a known benchmark for normalization and detection of diseases, the NCBI Corpus. The NCBI Corpus is a collection of around 800 PubMed Medline abstracts where disease entities were annotated and they were normalized or manually linked by experts to the medical subject headings taxonomy, giving rise to around 1,000 unique diseases identified by a unique mesh concept identifier. And the corpus itself comprises around 200,000 tokens. The mesh taxonomy, as I said, is a taxonomy. It's very large. It doesn't cover only diseases. We consider only its disease branch, which covers around 8,000 clinical diseases and conditions, which are the nodes of these three. It asserts quite a number of pieces of information, so rich disease metadata for each such concept, and it also provides a gloss or definition of the concept in the form of a short text of 10, 20 tokens. An example here of NCBI Corpus. So here you see an annotation of adenomatous polyposis coli, a kind of cancer. So it has been identified and it has been normalized to the identifier of the below entry corresponding to ID D011125, where you can see the canonical name, the scope note, so a gloss or definition of the disease, entry terms, so synonyms for this canonical name. There's some additional information as well. Important to notice here is that it also assigns a location of this concept within the mesh taxonomy, within the tree. For name entity recognition, we used a variant of a known current state-of-the-art model, the BioLSTM CRF model, with the main difference that as input embedding layer, we used BioElmo embedding from Peterson. For entity linking, we use this general architecture where on the one hand, the name entity is run over the corpus to identify the entities, then the Elmo embeddings of the constituent tokens are retrieved, linearly combined. In parallel to this, a node embedding using graph embeddings is computed over mesh. These two embeddings are fed then into a linear layer followed by a softmax layer, which it's taking charge of predicting the corresponding concept UID for this embedding pair. And this last part is the entity linking model. No, now for the fun part. We use two kinds of graph embeddings. On the one hand, node-to-back. Node-to-back relies first on an algorithm that does random walks on the graph. So in this case, the mesh taxonomy generates paths, and then these paths are inputted into skip-run model to generate an embedding. And we consider two variants of this. One where we only took into account the tree structure, and one where we lexicalized it in a way by basically starting the output embedding matrix with the Elmo embeddings of the scope nodes of the nodes. And important here to notice is that both the mention and the node embeddings were pre-trained. So the second variant were graph convolutional networks. These are generalizations of convolutional neural networks to graphs where filters are applied to neighbors of a node in a graph. Using this equation, I won't delve into it. Please look at the paper. Important here to notice that now the graph embedding is not pre-trained anymore, but it's trained together with the entity linking model. So for the results, our name entity recognition model achieves state-of-the-art results compared to the state-of-the-art for this corpus using a different model, a more simpler model, the Lamp et al. In 2017. This is a model where instead of input bio-Elmo embedding, you consider in corpus word-to-get embedding combined with character encoding of token. So we achieved 0.87 F1 scored as opposed to 0.84. Our results for entity linking were a bit less mitigated. We were able to identify node-to-back lexicalized as the best model. The model achieving the best performance in all the performance metrics. Combine the structural information with information from the lexical nodes. However, we were not able to beat the current state of the art for this corpus, which was published more or less at the same time as us, and that doesn't use graph embeddings at all, so Norco system, because we were stuck at 0.72 F score as opposed to 0.84. We also perform a multitask learning experiment, and we were able to observe that multitask learning increases name entity recognition performance further, but doesn't have impact on entity linking. As for the errors, for the name entity recognition, well, in some cases, entities were only partially detected, not fully detected. For entity linking, what happened is that often the model confused close neighbors with the intended target concept UID of the NCBI mentioned. As you can see here in this example, B-cell non-Hodgkin's lymphomas is normalized first correctly, but then it's normalized or linked to its child and then to another form of cancer when dealing with different variants of this entity, different synonyms. So conclusions, we adapted graph embeddings that explore both mesh, hierarchy, structure, and the description of diseases for entity linking. We combine entity recognition and linking models using multitask learning setting. The main findings are that node lexicalization improves all the structural lexical embeddings, although it doesn't yet achieve state-of-the-art results. Bio-Elmo led to large gains in entity recognition, so achieving a state-of-the-art. Multitask learning leads to better performance for name entity recognition. So as for the further work, we plan to incorporate the optimizations described in the Normco system, and we also plan to enlarge the target mesh taxonomy by linking it using linked data to larger knowledge graphs such as Wikipedia, because mesh is small, and we think that graph embeddings will work better on larger taxonomies. That's it. Thank you very much, and see you in the QA session.